Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 10, Operations with Numbers in Scientific Notation. Okay, so when they talk about operations, for starters, operations are addition, subtraction, multiplication, and division so far. So the speed of light is 300 million meters per second. The sun is approximately 1.5 times 10 to the 11 meters from Earth. How many seconds does it take for the sunlight to reach Earth? The first thing I want to do is find the speed of light in terms of scientific notation. So I'm first going to take 300 million and represent it as scientific notation. Now keep in mind that scientific notation is some number times 10 to the power of some magnitude. And d, by rule, has to be greater than or equal to 1, but less than 10. So what that means is the number to the left of the decimal can't be greater than 9, and it can't be 0 or less. So if I have this number here, to satisfy the D rule, I need a 3.0. So the number to the left of the decimal satisfies this. 3 is greater than 1, and it is less than 10. So there's my location of my decimal, and then I multiply it by 10 to some power, and the magnitude is how many spaces I had to move it from the decimal to where it has to be to make this equation true. So if I move the decimal from here, I go 1, 2, 3, 4, 5, 6, 7, 8 places. So 300 million is 3 times 10 to the 8th power. Now that I've done that, and I know that the sun is this many meters from Earth, we're talking about a problem with distance. Okay, so I'm going to use the equation distance equals rate times time. It won't be the first time you've seen this, and it won't be the last. So I'm going to use this equation to explain this and set up a problem. So our distance, it says how many seconds does it take? That's t. We're trying to solve for t here. So we must know two things and have to find the third. So the sun is so many meters from Earth. That's distance. So here is our d. And when I say d, I don't mean this d here, by the way. It's distance. Distance is 1.5 times 10 to the 11th power. That's the distance the Earth is from the sun. And that is going to equal the speed of light times time. And the speed of light is right here, 3.0 times 10 to the 8th power. And then I'm going to multiply that times t, or time, and that's what we're trying to solve for. Now, in order to solve an equation for a variable, it's called isolating the variable, we have to do the inverse operation. And we have multiplication, and the inverse of multiplication is division. So to solve this problem, I'm going to divide both sides by 10 to the 8, 3 times 10 to the 8. To make the equation still equivalent, you have to do the same to both sides. Okay, so if I divide both by 3 times 10 to the 8, this is still equal. I'm going to put an equal sign here. 3 times 10 to the 8 divided by 3 times 10 to the 8 is 1. 1 times t is just simply t. And that's our time, and that's what we're trying to solve for. 1.5 divided by 3 is 0.5. 3 goes into 1.5, a half a time. Okay, and then our rule for division is to subtract our exponents, and I'm going to show that so we remember the rule. So my answer is going to be 0.5 times 10 to the 11 minus 8, which is 3. That tells me to move the decimal 3 places to the right, so I'm going to get 500. 5 is 1 place, so that's to here. The decimal was here. 1, 2, 3. So 500, and it's seconds. How much time? 500 seconds. Now there is a way to represent our unit of measurement throughout. We're going to visit that soon, but I'm not going to address it in this lesson. So the answer is 500 seconds, which is just under 10 minutes, 9 minutes, somewhere around there. Okay, exercise 2. Now it says the mass of the moon. Let me get this out of the way. It says the mass of the moon is about this. 7.3 times 10 to the 22 kilograms. That's how big the moon is, how much the moon weighs, its mass. It would take approximately 26 million moons to equal the mass of the sun. So I'm going to write a sentence here, a mathematical sentence. The mass of the sun equals this number, 26 million times the mass of the moon. It takes 26 million moons to equal the mass of the sun. That's what this says. Mass of the sun is 26 million times the mass of the moon. Now I'm going to substitute in my givens. The mass of the moon is 7.3 times 10 to the 22, and we know the seconds, so we want to solve for the mass of the sun. So I am first going to convert this 26 million into a scientific notation. Let me stick with the same color. So if I take 26 million, that's a 0, to satisfy the rule, it's 2.6. This is a little crowded. Let me move it down. 2.6 times 10, and the decimal is here, and it's got to be moved here. So if the decimal's here and I got to move it this way, then how far is that? 1, 2, 3, 4, 5, 6, 7. So this is 2.6 times 10 to the 7th power. So I'm going to replace that with this. Okay, so we're trying to find the answer to the mass of the sun. I'm just going to use the letter m for that. So now I'm just going to simplify this. I'm going to say m equals, the mass of the sun equals 2.6 times 10 to the 7 times the mass of the moon, which we were told is right here, which is, so keep that neat. We're multiplying by 7.3 times 10 to the 22. Okay, so the mass equals, we're going to multiply these two numbers. So 2.6 times 7.3 equals 18.98 times 10, and we have an exponent here and an exponent there, and we are multiplying, and the rule says to add our exponents. So now we have the mass of the sun equals 18.98 times 10 to the 7 plus 22, which is 29. Now we have to keep in mind our rule for our d, which is up here. D has to be between 1 and 10, but it can equal 1, but it has to be less than 10. 18 is not less than 10, so I have to move the decimal over. So m equals 1.898 times 10. Now it was 29 places away from its ending location. Now we moved it left one. That's one more away from where it has to be, so we have to add 1 to our exponent. And the answer is 1.898 times 10 to the 30 kilograms. Okay, exercise 3 says the mass of the Earth is 5.9 times 10 to the 24 kilograms. Okay, the mass of Pluto is this really big number in kilograms. Compare to Pluto, how much greater is Earth mass than Pluto? Okay. So if we have Earth's mass and we want to know how much greater it is, that'd be like saying how much greater is 10 than 8? We'd say 10 minus 8 equals 2. 10 is 2 greater than 8. So we're going to take the Earth's mass and subtract Pluto's mass to equal their difference. That's what this question's asking. So the Earth's mass is 5.9 times 10 to the 24 kilograms, and the mass of Pluto is this number, Well, I need to convert this to scientific notation, so it's going to be 1.3, and there's 3, 6, 9, 12, 15, 18, 21, and then one more. So this is times 10 to the 22. So if I subtract 1.3 times 10 to the 22, okay, so I'm going to do this vertically. I prefer to do math vertically. So that's kilos also, kilograms, and I'm going to subtract. So when I subtract these two, 9 minus 3 is 6, 5 minus 1 is 4. I cannot subtract these here, so now I've got a problem. I cannot subtract if my exponents are different. So now I'm going to have to convert this, so I'm going to stop here because these are not the same. And I can either move one left to, or I can move the other right to, and it doesn't matter which one you do. Okay, so if I move this decimal 2 places to the right, I'm moving closer to where it has to be, so every time I move this decimal to the right, this value decreases. So if I need to move it 2 decimal places to the right to decrease it to 22, so that'd be 5. The decimal was here, here's 1, here's 2, so now I have 590.0 times 10 to the 22, because I've already moved it 2 decimal places closer to where it has to be, so I subtracted 2 from my exponent. I'm now going to subtract this 1.3 times 10 to the 22. Be careful how you line up your decimals. So everything, you're subtracting tenths from tenths and ones from ones and so forth. So when I subtract, my powers don't change. And I'm going to have to borrow from the 9. That would become 9. And this is 10 minus 3, which is 7. 9 minus 1 is 8. 8 minus 0. And finally 5 minus 0. So it's 588.7 times 10 to the 22. Okay, that is not in scientific notation. I need a number between 1 and 10. So I need 5.887 times 10. Now I moved the decimal 2 places to the left. That is further from where it has to be, so I have to add 2 places to my exponent, and the answer is 5.887 times 10 to the 24 kilograms. That is how much, compared to Pluto, that's how much greater the sun's mass is. Okay, exercise 4. This one I'm going to have to go back and get some information. It says, using the information in exercise 2 and 3, find the combined mass of the moon, Earth, and Pluto. So the moon plus Earth plus Pluto equals a total. Okay? So I'm going to write it this way. I just want to have the number, the thing that I'm solving for all by itself on the left. It just feels better to me that way. So the total equals these. So now I need the mass of the moon. And it said to use the information from exercises 2 and 3. So if I go back to exercise 2, okay, the mass of the moon is 7.3 times 10 to the 22. So that is 7.3 times 10 to the 22. How about I color code all of these so you see what's going on here. So then I'm going to do plus Earth mass plus Pluto's mass. Okay, so now I need Earth's mass. So I have the total equals the Earth's mass which is red. I'm sorry, that's the moon mass, plus the Earth's mass. The mass of the Earth is right here. It's in lesson 3, so I don't have to, exercise 3, so I don't have to go back. And that will be, let me use black for my unit of, or my operation. And Earth is 5.9 times 10 to the 24. and then we're going to add Pluto's mass, which is right here in scientific notation. So Pluto's mass is 1.3 times 10 to the 22. Okay? All right, so that's what we're trying to do. So now I'm going to line these up vertically. And I have two that have 22s for magnitude, and I have one that has 24. They all have to be the same if I'm adding. So I'd rather add or get rid of two here and make them all 22s. That way I'm only changing one, and then we can change back or vice versa when we're done. All right, so I'm going to write this in vertically. So I'm going to write 7, but I changed my color, one moment. 7.3 times 10 to the 22. 5.9 times 10 to the 24. And 1.3 times 10 to the 22. I'm going to add these up, but I'm not going to do it here because these are not equal. So I'm going to convert these. And this time I'll go up and make this 24. And I'll show you the difference between the two. If I'm going to make this times 10 to the 24, I have to move the decimal 2 places away from where I'm ending up. So my decimal is now going to be before the 7, which would be 3, 7. It was here, so here's 1, here is 2. So it's going to be 0.073. I moved it 2 decimal places to the left, and now I'm going to change that to 24. I'm going to leave my 5.9 and line up my decimals. 5.900 times 10 to the 24. And then finally I'm going to convert this one so it's times 10 to the 24. And I need 1.3, and then I need the decimal to move 2 places to the left. So that's going to give me 3, 1. So here's 1, here's 2. So it's 0.013 times 10 to the 24th power. And now I can add them because my exponents are all 24. So when I add these, 3 plus 0 plus 3 is 6. 7 plus 0 plus 1 is 8. 9 plus 0 plus 0 is 9. And 5 plus 0 plus 0 is 5. And that is times 10 to the 24, because when we add, our exponents don't change. And since I moved it up to 24, I do not have to convert my answer like I did here. So if we work our way up to the larger number, our answer will be our final answer usually, depending on what our numbers are here, of course. If they added up to more than 10, then we'd still have to move it once. So there's exercise 4. That is the total combined mass of the Moon, Earth, and Pluto. Okay, exercise 5. How many combined Moons, Earths, and Pluto's mass, the answer to 4, which is right here, are needed to equal the mass of the Sun? Okay, so it's saying the mass of the Sun equals some number times the mass of these 3 things, which is 5.986 times 10 to the 24th power. Okay. So now we need to know the mass of the Sun to answer this question. So if I move back up here, the mass of the Earth, mass of Pluto, I need to search for the mass of the Sun. They did give it to us somewhere. The mass of the Moon, and determine the mass of the Sun. That was our answer to exercise 2. So here is our answer. Okay. So the mass of the Sun, this is the Sun, the mass of Sun is 1.898 times 10 to the 30 kilos. So I'm going to put this here. So to solve this, I'm just going to substitute now. 1.898 times 10 to the 30 equals x times 5.986 times 10 to the 24. Okay, let me use another value besides x. because we have x's in our multiplication when we do scientific notation. So let me use, I don't know, let's use y. So mass of the sun equals some number y times this, and therefore we substitute this in, and we're trying to find how many times this goes into that. So we need to divide. This is 30. Okay, so this is a multiplication problem. So in order to solve it, we're going to divide. We want y by itself, so we're going to divide by 5.986 times 10 to the 24th power. And what you do to one side, you do to the other. These will cancel, and it will leave me with y equals. Okay, so when I divided 1.898 by 5.896, I got 0.3219, so forth. I'll go out 4 decimal places. 0.3219 times 10, and since we're dividing, we subtract 30 minus 24. So I'm going to show my work here so we remember the rule. So that's going to end up being 0.3219 times 10 to the 6, but I don't have my, this is 0.3, and 0 is less than 1, so I need to move my decimal here to make it scientific, so it's 3.219 times 10. I moved it closer to where it has to be, so this decreases by 1. Okay, so the answer to this is, it would take 3.219 times 10 to the 5th Moon, Earth, and Pluto masses to equal the Sun. This can also be simplified because 10 to the 5th just means 5 decimal places. So if I move this 1, 2, 3, 3, 2, 1, 9, now that's 3 decimal places. Here's 4, here's 5, and that is 321,900 Earth, moons, and Plutos it would take to equal the Sun's mass. That is just amazing. Okay, that is the end of lesson 10. Go do your problem set.